So I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. So today we are going to see lecture number 13, applications of heat transfer. So before this lecture we had conducted 12 lecture. So in these 12 lecture we have seen that what is the mean by heat transfer, what are the modes or the types of heat transfer and how they vary with each other, what are the essential conditions to satisfy that their condition for heat transfer, and what is the major impact of the modes of heat transfer in our daily life and engineering applications. So right now dedicatedly we are going to see how each application will have overall all modes of heat transfer simultaneously working together in the same real life example and engineering applications. So I am Amraraj Sawant, assistant professor. Let's start today's discussion. Introduction. Heat transfer is essential in engineering, and why it is so? Because to analyze how efficient system may be, or to work out how the heat transfer will affect the mechanism of engineering problems or engineering applications. So it occurs via conduction, convection and radiation, as we have seen that these three modes of heat transfer are there, their respective working parameters and their working conditions are we have seen in previous lectures. So it is used in power, aerospace, electronics and more. So heat transfer is everywhere, and you can see any object, there must be some heat transfer going on, and until the temperature equilibrium or thermal equilibrium reaches. So we have seen these type of applications in short, but in this lecture we are going to see these application in details. So what is the significance of heat transfer in our day-to-day life or in engineering applications? We are going to see this. So optimizes energy use, means how much energy we have to save, that should be analyzed after using this heat transfer analysis, and enhance reliability, supports sustainability. So with this heat transfer like conduction, convection, radiation, we are analyzing the system, or we are analyzing as per the human comfort or human need for working out the engineering systems. So that system we are analyzing how we can enhance its efficiency, and while enhancing its efficiency we also minimizes the power consumption, and due to which we can have a sustainable system, so that as per the use we can get maximum efficiency out of our system or any engineering application. It is crucial for thermal efficiency and modern design, as I have explained it before. So we are going to see in details how these applications of heat transfer with their three modes are in a real life or in engineering application we are going to apply it. So heat exchanger in power plant. In first lecture I have given a brief introduction about power plant. I am going to recall it or revise it once again. A power plant is the plant where the electricity is generated, and how this electricity is generated by using the fuel as a coal. In India, maximum up to 70% electricity is generated by using coal. So by burning the coal we are giving the heat from that coal to the water, and that water is going to converted from water to steam, and that steam we are going to flow through the turbine, and while the turbine is going to rotate, the generator is also going to rotate, and that generator while rotating creates electricity. And that's why in our home and in your colleges you can have that electricity. So major portion of India, 70%, about 70 to 80% is the electricity is generated by using coal. So that power plant, in that power plant, the heat exchanger is needed. And why it is needed, just I have explained right now. To convert that water to steam, the boiler system is needed. And for that boiler system, or that whatever the water is going inside that boiler, it has to be preheated, because it is causing or it is having to have higher efficiency. If the water is preheated, then it is easier to us to achieve some higher efficiencies. So for preheating or for exchanging the heat exchangers are needed in a power plant. So let's see, they use in Rankine and Breton cycles. So these are the power plant cycles that you are going to see in a steam turbine engineering subject. So to transfer the heat between the fluids without mixing. What is mean by this? To transfer, just like I have said, that to transfer the heat from water, okay, which is at a cold side or at a cold temperature, then the exhaust gases, is a pre-mixing or preheating, or so without any mixing, they are just in a physical, not in a physical contact, in a convection mode, they are transferring the heat. So that's why the heat exchangers are needed. Here in this diagram you can see that these are the small tubes. Okay, in that small tubes water is flowing through it, and in this cylinder type structure there are some flue gases or exhaust gases which are having a higher temperature than ambient air. So the heat energy is flowing from these high temperature gases to these water, okay, to this water, and that water will be get heated, and again this water will fill or will go through the series of these heat exchanger, and that's why the water temperature rises. And before coming to the boiler, the water is having higher temperature, and that's why we have get some higher side efficiency by using this heat exchanger. So in heat exchanger, what are the modes of heat transfer will takes place? We are going to see this. Conduction through the metal walls, just like I have said that these are the tubes inside this cylindrical structure, and these tubes are getting in a contact with the flue gases. So through these metal tubes or metal walls, the conduction is going to happen. As in the first 3 lectures we have seen that what are the types and modes of the heat transfer. I am going to again recall it. First is a conduction, which is happen in a solid due to the intermolecular vibrations and free electrons. Second is a convection, which is happens with the solid and the fluid flow. Because of fluid flow, there will be the convection, which is we are going to calculate Q as with respect to convective heat transfer coefficient. And in radiation, the heat transfer takes place because of electromagnetic waves. And in details, that electromagnetic waves, the charge on the atoms and particles will vibrate with their central position with the speed of light. So that's why the radiation will have lesser time to reach any surfaces. So these 3 modes of heat transfer, we have seen that. So similarly, and these ideas or this concept we are going to implement in the real application. So the conduction through the wall metals, because the metal walls are solids, okay, and convection on both sides of wall means what? These metal plates and this cylindrical structure, okay, in between that the flue gases and water is just passing, means water which is having cold temperature and the flue gases having high temperature. So there the flue gases are flowing. So this is the case of convection heat transfer. And radiation is at high temperature system. When this water is coming from first heat exchanger, then it is going from second, then it is going from third, then it is going from fourth, and then it is again going from sixth heat exchanger. Then but obviously this water at this outlet will have higher temperature than this outlet, okay, because the heat is going to be added And so at this time the water, when it is getting into the boiler, and after that the boiler converts water to steam at a superheated steam. So that superheated steam will cause heat transfer in the form of radiation. So heat exchanger engineering relevance. So while optimizing the surface area, thermal conductivity and fluid dynamics, we can achieve more heat exchange. What is mean by this? So you can see here again, once again, by optimizing surface area, whatever the tubes are going to be inserted in this cylindrical structure, okay, so whatever the surface area of this tube are going to be contact in the flue gases for preheating of water to this power plant as a heat exchanger. So that surface area, if you increase that surface area, then there will be the more chances of heat transfer. Why? Because in convection heat transfer we have seen that the Q, which is total heat transfer, is depends on H multiplied by AS multiplied by TS minus T infinity. So where AS is a surface area. If you just increase the surface area, if you increase this surface area, then heat transfer will also going to be increased. So that's why the surface area is a main parameter where you can have more heat exchange. So thermal conductivity, it is a property of material, so by which in a conduction heat transfer you can get more heat transfer. So how it is? So similarly we are going to apply Fourier law for thermal conduction, and by Fourier law Q is equal to minus K dt by dx. So if this K value is higher than this Q value, means heat transfer rate is also higher. So simple these equations we are going to apply in general life. So that's why the basic is important. If you are completely understanding or completely clear with your basic, then you are easily going to apply these to the engineering applications or real life applications. So here use of LMTD and overall heat transfer coefficient. So use of LMTD for temperature measurement, where the temperature is going to increase or decrease and at what rate or what average. So we are calculating in this LMTD, and this is a mathematical form you are going to see in your course subject as a heat transfer. And overall heat transfer, so what is mean by here overall heat transfer coefficient? We have seen that for conduction, thermal conductivity plays an important role for conduction. For convection, convective heat transfer coefficient plays an important role. And for radiation, the sigma, which is Stefan-Boltzmann constant, plays an important role to calculate, or these will impact how much heat will going to transfer. And as the name suggests, the overall heat transfer coefficient means with consideration of these three modes and these three parameters. Likewise, with a conduction, convection and radiation, the overall heat transfer coefficient is going to be calculated for analysis of the system in the real world. Okay, we are just before in lectures we have calculated how the resistance in conduction, in convection and radiation, but in actual practices, as I have said, that all three modes are simultaneously acted upon that object or that application. Likewise here a heat exchanger is there, so in heat exchanger all three modes are present, and so for all that three modes the coefficient needs to be calculated, and this overall heat transfer coefficient is calculated by using this thermal conductivity heat transfer convective heat transfer coefficient and this Stefan-Boltzmann law. So with these you can have overall heat transfer coefficient, and its mathematical form and derivative in this course is not needed. Here just a brief introduction or short introduction to this overall heat transfer, and what is mean to say the overall heat transfer coefficient is just I have explained. So heat transfer from steam to the feed water. This is the specific shell and tube heat exchangers which transfer the heat from steam to water to increase the temperature of water. So just keep in mind that heat is always transferring from higher energy level to the lower energy level by second law of thermodynamics, and if you want to reverse this, so you need an external work. So in shell and tube type heat exchanger, we just transferring the heat from steam to water, because the steam which is having higher temperature and water is having lower temperature, so the heat transfer will get taken place from higher side of steam to the lower side temperature of water, and that's why the water temperature will get rises. So heat exchanger improves efficiency and reduces fuel usage overall in a power plant. So next application of heat transfer is refrigeration and air conditioning. So as far as you know that everyone you are familiar with air conditioning system, it does according to the human thermal comfort, it does temperature variation, or it controls the temperature and extract the heat from that constrained space, or you can say a room. Okay, so for that in refrigeration, the main principle to extract the heat is heat transfer, or you can extract the heat from that specified room or controlled space. By for extracting that, you have to analyze how that heat should be is generating. It is generating from human, or it is generating from any electrical appliances, or it is heat is there because of some thermal radiation from outside. So that heat should be calculated, and that heat, whatever the amount of heat is there in your room or in that constrained space, so that heat if you analyze, then according to that you are going to install your AC unit. So otherwise let's say the 100 watt of heat energy is there inside room, and you are installing air conditioning which is having capacity of 10 watt, then it is not efficient way to extract that heat, na? So that's why you have to compare how much tonnage capacity of air conditioning I am going to install according to your requirements. So similarly, here includes evaporator, compressor, condenser and expansion valve. These are the components of refrigeration and air conditioning system. So these all components will work according to their working, but the main principle of heat transferring or heat exchange is there, and these three modes of heat transfer are applied here also. So refrigeration heat transfer modes. In evaporator, convection heat transfer takes place. Evaporator is a part of a refrigeration, so where the evaporation takes place and the heat is going to be absorbed from the surrounding. So in the evaporator, what is going to happen, the surrounding is at a higher temperature, and the evaporator where the liquid refrigerant flows, so the heat, as I said, the heat is always flow from higher energy level, that is higher temperature, to lower temperature by second law of thermodynamics. So that's why in evaporator the heat is going to transfer from higher temperature to the evaporator which is having lower temperature. So by the use or by the virtue of convection heat transfer. And what is the convection heat transfer? The fluid flows over the solid surface, and here the solid surface is of evaporator and fluid is a surrounding medium. So in condenser, convection and conduction both are together happens. Likewise in the first lecture I have given example of cooling tower. So in a condenser, convection and conduction both simultaneously occurs, and minor radiation outwards. So you can see that refrigeration and air conditioning system, the main purpose of these refrigeration and air conditioning system is to minimize or to extract the heat from that constrained space or your room. But where does the radiation comes? Here the radiation comes from the outside part where the heat is extracted and heat is delivered to the atmosphere, that heat delivery to the atmosphere, there the radiation heat transfer you can observe. So in refrigeration, the higher, for getting higher COP, that is coefficient of performance, or energy efficiency, or environmental safety, or we can use fins to enhance or to increase the surface area, the airflow, refrigerants with the optimal properties. So all of these, if you manipulate or you design according to your condition, then you can get a higher efficiency. And for these, for getting the higher efficiency or environmental safety, or the whatever the airflow is there, or refrigerant to optimize their properties, you must have to understand what type of heat transfer is going to take place, how much heat transfer is going to take place. So both of these are needed. So the basic thing is there, you first have to calculate what type of heat transfer is there, and second of all, how much heat is going to transfer from one system to another, and according to that you have to design your specified component. So in refrigeration, like in split AC, refrigeration and air conditioning, in split AC, the heat from the room is absorbed and carried outside, and it is rejected. It is just simple working of the split AC, and that heat is just absorbed and delivered to the outside. And what types of heat transfer modes are acted, we have just seen it. So aerospace in thermal protection, this is one of the most important application of heat transfer in engineering life, and this is our daily life also. So used in a spacecraft and re-entry vehicles and high speed aircraft. I have given this example many times in the lecture before. So here you can see that the spacecraft or the shuttle is re-entering from vacuum to, or from space to Earth's atmosphere, and due to the friction, the large amount of heat is generated. And here you can see that this bottom side, you are seeing that the black structure or black coating or black material is there, and here in upper side that coating is not present. And why it is so? Just not to look aesthetic for black and white, it is not for just aesthetic view. It is actually a thermal coating or thermal shielding. Why? Because the higher amount of heat is generated at this bottom, and if this heat will as I said, the heat transfer will always takes place from higher side to lower side, and if this heat will come inside or transfer inside this component of the spacecraft, then these components may fail, and due to the failure the aircraft may fail. So to avoid this, the insulating material is provided at the bottom and at the nodes, so that the heat transfer will be minimized. So this is main very important application of heat transfer. And for calculating this, really a complicated modeling should be done, and for after that the analysis is done. So these complicated structure, just like we have seen in a fourth lecture, one-dimensional steady state heat conduction equation and three-dimensional steady generalized equation. So you have to apply here a three-dimensional generalized equation with time variation. It is not a steady state with a time variation, so it is a complex problem. So that's why the heat transfer is the most important subject in your engineering, to analyze the system design. So it protects from frictional and solar heating. Whenever the spacecraft is entering to our Earth's atmosphere, then it is due to the frictional force the heat is generated. But when the spacecraft is in a vacuum, then in vacuum only radiation heat transfer will takes place, and so that the solar heating, the radiation coming from solar, that also has to stop, or that also heat transfer has to stop from outside to inside. So that's why this thermal coating or thermal protection is given to the spacecraft. So what types of heat transfer mode, just I have explained you, just you can recall here. So radiation is a main space mechanism where in space there is a vacuum, so that's why only radiation heat transfer takes place. So in conduction within the material, likewise the internal components of spacecraft will carry away the heat from the outside, is a conduction phenomena. And in convection during re-entry, just I have said that for in convection the air which is flowing like this, and the spacecraft with a high speed it is entering in at Earth's atmosphere, due to which the flow of these fluids, the high frictional force is created, and due to this high heat can be observed here at the bottom and at the nose. So aerospace engineering relevance, what is the relevance? So at high temperature material, insulation, abrasive shield, and again model heat flux gradients. So these are the things you have to analyze, and for analyzing these things you must understand the basic of heat transfer, what types of modes are there, and again how much in a quantity the heat transfer is going to be. So example, the NASA Orion and SpaceX Dragon uses ablative shield to withstand 1500 degrees Celsius during re-entry. So just imagine that water is boiling at 100 degrees Celsius, and we are talking here 1500 degrees Celsius temperature that is to be restricted while re-entering the shuttle or spacecraft, that is restricted, and so that temperature is withstand to not to fail the internal components of the spacecraft. That type of material is used in NASA Orion mission and SpaceX Dragon mission. So you just think that what types of material are going to be used in this insulation. So really the heat transfer is a subject like you can't imagine that how the process should be, and there are lots of possibilities to do the research in this field. So thank you very much for today's lecture. I conclude this lecture here. So you will have an assignment of 20 multiple choice question over this lecture, and it is I am going to publish it in a discussion forum, and online link is given to you. So thank you very much.